these, and I can write it as tau r. So I can rewrite the balance as minus tau r 2 pi r dr plus d by dr tau r 2 pi r dr into dx. Did I get it right? Yeah. 2 pi r dx. Sorry. 2 pi r dx. Okay. So I can open it up and write it in Taylor series expansion. So the variation of radius, remember that it's a varying cross sectional area, so it has to be preserved inside the differential. Okay. Plus dx 2 pi r dr minus 2 pi r dr plus dp by dx 2 pi r dr into dx. That should be equal to 0. Okay. So now, so that will be minus d by dr r into tau r plus that should be equal to dp by dx. So that's the force balance. That's the force balance. Okay. What is tau r? So be very careful about the sign that you have. When you are actually using cylindrical coordinates, it's not the same as what you have in Cartesian coordinates. So remember that in Cartesian coordinates, in flat plate case, if you look at the flat plate, okay, the wall is actually, the effect of the wall is actually in the positive y direction. But when you take a tube, the effect of the wall is actually in the negative r direction. So remember that if you take a, so compare that with the tube. So if this is the center, so the positive r direction is going outside from the center. So the wall is now actually located at r equal to r naught. Therefore, the effect of the wall is actually in the negative r direction. That's why you have a minus sign. So be very careful when you go from Cartesian to cylindrical coordinates or spherical coordinates. You should always be very careful about the sign that you use. Okay. So therefore, so if you plug that in, it will be mu into d by dr r du by dr equal to, oh, I forgot an r here, r dp by dx. So the r doesn't cancel out because it's present inside the differential. It should be r dp by dx. Please correct it. Okay. So mu by r d by dr into r du by dr equal to dp by dx. So that gives you a balance for the velocity in the fully developed regime. Okay. So this is not true in the developing or the entry regime, it's true only in the fully developed regime. True only in the fully developed regime where dp by dx, the pressure gradient, is not a function of the radial position. Therefore, you can find out the velocity profile in the fully developed regime. How do we find the pressure gradient? Is it a measurable quantity? Yes. How? We want pressure gradient in the fully developed regime. So how do we find the pressure gradient? How many of you have heard this friction factor? Friction factor, right? So if you know the friction factor, friction factor is actually defined as F. Okay. If you know friction factor is actually related to the pressure gradient in the fully developed regime. So if you know the friction factor, then you should actually be able to estimate the pressure gradient. So that's given as minus dp by dx into d divided by rho. So that's the friction factor. How is the friction factor and friction coefficient defined? What's friction coefficient? So friction coefficient, that's Cf, that's tau divided by rho um square by 2. How are these two related? How are these two related? Yeah, they are not same, this definitely not same, but how are they related? So this is, so for laminar flow conditions, it actually turns out that it's 4 times Cf. Okay, this is only true for laminar flow. Okay. Now, if you are looking at turbulent flow and other conditions, there are some correlations which is available for the friction factor, which is in terms of the Reynolds number. And so that's given by, so for laminar flow, so this 4 times Cf approximately translates to 64 by the Reynolds number. Reynolds number is defined based on the diameter of the tube, not the radius. Okay, so RED is defined as rho um d by mu. So which means that the Reynolds number does not change with the location. Okay, so it's defined based on the mixing cup velocity. Okay, and for turbulent flow, it's given by 0.316 into Re e power minus half, and this validity is when it is less than or equal to 2 into 10 power 4. What's the transition Reynolds number for pipe flow? 2000, 2100 ballpark, and and this is valid when Reynolds number is greater than 2 into 10 power 4. So that's the correlation for turbulent conditions, and if you know the friction factor, you should be able to estimate the pressure gradient. Okay, so if we know the pressure gradient, we should be able to integrate the expression and find the velocity profile, and that's what we are going to do now. So we can integrate this expression here. Okay, so the integral will be, I can do it here. So I can integrate this expression, so it will be R du by dr, that's equal to 1 by mu dp by dx into r square by 2 plus C1, and u is 1 by mu dp by dx r square by 4 plus C1 ln r plus C2. So that's the integral. What are the boundary conditions? R equal to 0, so du by dr at r equal to 0, that's equal to 0 because of the symmetry. Okay, and what about the other boundary condition? U at r equal to r naught is 0. Okay, so now if I put the first boundary condition, which constant will disappear? C1 will disappear, right? So we can say that, so du by dr at r equal to 0, so that means C1 is 0, so that constant will go to 0. Okay. Now if I put the second constant, u at r naught equal to 0, so that will be 0 equal to 1 by mu dp by dx into r naught square by 4 plus C2. So C2 will be minus 1 by mu dp by dx into r naught square by 4. So from this I can find the velocity profile, that will be 1 by mu dp by dx, so I can pull 4 out, 1 minus r by r naught the whole square. Okay. So note that I have pulled a minus sign outside. R by r naught is greater than 1 or less than 1? it's less than 1. So why is there a minus sign? Because dp by dx is negative, right? So this is the velocity profile with respect to r. So here clearly we show that it's not a function of the x position because the velocity profile doesn't change, and so dp by dx has to be constant, right? So dp by dx has to be constant for a steady flow, and therefore it has to be a function of only the radial position in the fully developed region. We still don't know what happens in the entry region. We'll come to that later. So from here, now we should be able to find out what is the average velocity profile. So um, which is the mixing cup or the average velocity profile, is 2 by r naught square integral 0 to r naught u into r dr, right? So I can substitute now the velocity profile. So that will be 2 by r naught square naught 1 by mu 4 mu dp by dx I am not going to do the integration here, I'll just give you the final expression. So the integral will be minus 1 by 4 mu dp by so that will be r naught square by 8 mu into dp by dx. Okay, so that will be the average velocity. So now I can use that as a scaling. Remember, we defined average velocity for scaling purposes, right? So if I know dp by dx, I'm done. I know my cup mixing velocity, and so I now know the scaling velocity. So now I can use that to scale my actual velocity profile. So therefore, u by um is now given by 2 into 1 minus r by r naught the whole square. So that's the velocity profile in the fully developed region. Okay, is that clear to everyone? Any questions on this so far? Okay, so now the purpose of all this exercise, remember that in this course the purpose is to find the heat transport coefficient and the mass transport coefficient. So what we are really interested in is the thermal boundary layer and the concentration boundary layer. Okay. But the momentum boundary layer, they have a strong effect on the thermal and the concentration boundary layer. So once we know the velocity profile, now we can proceed and find out what is its effect on the thermal boundary layer. So what we are going to see next is the thermal boundary layer. So how do we characterize thermal boundary layer when there is a fluid which is flowing through a pipe? Okay. So I have a pipe here, and this is R, and this is X. Okay. So now when it comes to heat transport problem, so there are two specific cases that one can sort of think of, right? So one is you can maintain a constant flux of heat that is actually removed from that surface. Okay. So first case would be, case 1 would be, I have a constant surface heat flux. Okay. So I can have a situation where the flux of heat that is either removed or given to the cylinder or given to the tube is maintained constant. So if it is at a higher, if the fluid is at a higher temperature, then there is a constant flux at which the heat is removed, and if the fluid is at a lower temperature where you want to heat the fluid, then it could be that there is a constant flux of heat that is supplied to the tube. Okay. So if I say that the fluid is now flowing inside the tube, and if I assume that it's a flat velocity profile before it enters the tube, and if I assume that the temperature is T infinity, okay, so that's the temperature of the fluid before it enters the tube. Okay, so now similar to momentum boundary layer, I'll also have a thermal boundary layer, okay, where the effect of the surface is felt by the fluid as soon as the fluid enters the tube, and up to a certain location only if a fraction of the fluid in any cross section is experiencing the presence of the wall or the heat transport from the wall, and up to a certain location, and a location called fully developed thermal fully developed region. So at that location, every fluid particle in the cross section will now experience the presence of heat transport from the wall to the fluid, or vice versa if the temperature of the fluid is hotter than the surroundings. Okay. So now similar to momentum boundary layer, we can define a thermal boundary layer and also a regime for fully developed thermal boundary layer condition. So now what will be the temperature profile? Suppose I take x1. Okay. So I want to draw the temperature profile. So let's say that this is the boundary layer location. Okay. And the temperature, if I assume that the heat is being supplied to the fluid, okay. So now what will be the gradient, what will be the flux at the boundary? Will it be positive or negative? So heat is being supplied from the surroundings to the fluid, negative flux, okay. So now okay, so that's the temperature profile. So note that this is the temperature profile, okay. This is the temperature profile, and there is a constant flux at the boundary. Okay, so this is the center, that's R equal to R naught. Okay. Now supposing if I take a second case where I maintain the boundary at a constant temperature, I can always do that, right? So what happens in the fully developed regime? What happens in the fully developed regime? What will be the temperature profile? Yeah. So this is at x1. What about fully developed regime? So supposing I have a x greater than the fully developed location, there is no boundary layer, okay, because the fluid particle at every location in the cross section is now experiencing the presence of heat transport from the wall or to the wall, okay. So which means that so there will be a temperature profile which looks like this, okay. Is this a function of axial position? Remember in velocity boundary layer, we said moment it touches the fully developed regime, the velocity profile doesn't change. What about in the case of thermal boundary layer? Yeah, same? No. Even here, you will have heat that is being supplied to the fluid, right? So how can you have a same temperature profile? So the temperature profile, the local temperature profile is now going to be a function of both x and r in the fully developed regime, unlike what you saw in the momentum boundary layer. So this is a significant difference from as compared to what you saw in the flat plate case, flow past a flat plate case, where all three boundary layers have a similar profile. But in case of a pipe flow, the local temperature profile is now going to be a function of both x and r. But then what is interesting is that you can still do something, yeah? No, it's not necessarily linear. Not necessarily it's linear. We will actually show it rigorously that it need not be linear. So what you see is, you will see what is called the profiles will be similar. Okay? We will actually mostly in tomorrow's lecture I'll actually show you how to see that the temperature profiles are similar. It's not very obvious. If you look at the profiles here, it's not very obvious what you mean by similar profiles. So what you will have is similar profiles. So in any location after the fully developed regime in the thermal boundary layer case is that you will have similar temperature profiles. So note that they are not same, it's only similar. So we're going to define what is meant by similar profile, not in today's, mostly in tomorrow's lecture, okay. Alright, so now once we know this, we can go to the next case where you have a constant temperature. So supposing I maintain the surface temperature at a certain constant value, okay. So now I have a tube here. Once again I have a boundary layer, thermal boundary layer, thermal, and I maintain the surface temperature as constant. Okay. So now I can draw a profile, let us say at some location x1. Okay. So that is a constant temperature. So this is at position x1, which is less than the fully developed regime, and if I look at the profile at the fully developed regime, so once again that is a temperature of the surface, and as you go past into the pipe, there will be continuous transport of heat from the wall to the fluid, and so there will be a change in the temperature profile. Once again this will be a function of x and r, but what you will see is that you will get what is called a similar profile, and we are actually going to capitalize on this aspect that the profile is similar, and we are going to attempt to solve the problem and get the heat transport and mass transport coefficient, okay. So before that, before we even understand what is a similar profile, we need to have a reference, right? Yes. Because even if you have constant temperature, you have a flux of heat transport, right? So until the fluid temperature equilibrates, right, because of Newton's law of cooling. What's Newton's law of cooling? At the local point, the flux is given by some heat transport coefficient into the temperature difference, right. So till the fluid equilibrates with the wall temperature, there is going to be constant addition of heat from the wall to the fluid. So therefore there is addition of capacity to the fluid, and so you will see that the temperature is going to change with x location in the fully developed regime. This is fundamentally different from what you saw in the momentum boundary layer, but we will see that because of the similarity or the profile is similar, you will see that there is some intuitive way by which you can actually solve this problem. So in order to define similar profile, we need to define a reference temperature, okay. Just like how we define mixing cup velocity, we can also define what's called the mixing cup or the average cross-sectional average temperature. So how do we define this? What's the conserved property? So remember, in the velocity boundary layer we use the mass flow rate as the conserved property. So what do we do here? So you use what is called the internal energy in a given cross section. So you use the property of internal energy at a given cross section to define the cross sectional average temperature. So the internal energy at any location is given by integral over the cross section rho times the capacity of the fluid, internal capacity of the fluid, which is rho Cv multiplied by U into T into dAc, right. So that is the internal energy that is actually being transported. So now we can define this as rho into Cv into, in terms of the mixing cup velocity multiplied by the average temperature into the cross sectional area. So note that it's a definition. We define the average amount of heat that is actually stored in the fluid at any cross section is given by the capacity multiplied by the mixing cup velocity multiplied by the mixing cup temperature multiplied by the cross sectional area. Okay. So now, so from here we find Tm is 1 by rho Cv um AC integral over the cross section T into dAc. Okay. So I can, dAc is nothing but 2 pi r dr. So that will be 2 pi into rho Cv if it is incompressible fluid um AC U into T into r dr, 0 to r. Okay. So from here we can deduct that Tm, we can deduce that Tm is 2 pi divided by um into cross sectional area is pi r naught square into integral u t r dr 0 to r naught. So that will be 2 by um r naught square r dr. So that's the definition of mixing cup or average temperature profile at any cross section. It's called the mixing cup or average temperature Is this a function of x position? No. Why? Doesn't matter whether it is constant flux or constant temperature. Is this constant with respect to x position? Depends whether t is a function of x and r, right? So this integral is only a function of r. So this obviously has to be a function of x position. Unlike what we saw in the velocity boundary layer, the mixing cup temperature is now a function of the x position. Okay. So what we will do in the next lecture is, we will start by defining what is called a similar profile. Okay. And that definition we will capitalize on the fact that the mixing cup temperature is also a function of the axial position. We will show that the temperature profiles in the fully developed regime is very similar, and with that we will be able to solve the equations and we will be able to find the heat transport coefficient. Okay.